We are continuing our conversation about chemical kinetics with the organizer on page 903. We were filling in the far left-hand side. We left off with something called potential energy diagram. So we're going to pick up there with this second video. And so potential energy diagrams are a way of showing how energy changes within the molecules as we move from reactants to products. And we have also learned that there's something called an activated complex that can also appear in a potential energy diagram. Because there are two ways that energy changes, there are two different kinds of potential energy diagrams. So can you guess what those two types of reactions are? Hopefully you've come up with one of them being exothermic, where we show a release of energy, and the other endothermic, which is the absorption of energy. So we're going to shift gears from the organizer on page 903 to the organizer on page 909 because that focuses strictly on potential energy diagrams. So that's what we're taking a look at. So in a potential energy diagram, you are going to be able to look at the enthalpy of reaction, the activation energy. We're going to take a look at the idea of a reversible reaction, and then we'll eventually get into the idea of catalyst. So all of these things are going to influence potential energy diagram. So let's start with the exothermic potential energy diagram. So notice that the axes, you've got energy on the y-axis, you've got the reaction coordinates on the x-axis. So that's really just a version of time. So you always start off with reactants, you move through the activated complex to the products. So let's just say that our reactants are starting off with 100 kilojoules here. Okay, in order to get to the activated complex, in order to get those molecules, remember in the one video we saw that you had A and B, C reacting. Well, that activated complex was the point where you were trying to form this one and break this one. And the activated complex was something in between. So because B has more bonds than it should, it is a very unstable molecule. It doesn't like to stick around very long, so it transitions pretty quickly once it's made. So if you add enough energy to create this transition structure, this activated complex, you're going to transition pretty quickly to move on to the products. So let's just say that this is at 130 kilojoules, our activated complex. So the activation energy is the amount of energy that you have to add to get to the activated complex. It's always going to be positive. And in this case, if I'm starting at 100 and moving up to 130, it's going to be plus 30 kilojoules of energy. Once I've hit that activated complex, now I can continue on down and create my products. Notice that this is exothermic, so my delta H is going to be negative. My reactants possess more potential energy than my products. So to go from my reactants to my products, I'm giving off energy as a result. So the delta H is going to be negative because it's an exothermic process. And if this were at, let's say this is at 20, what's my delta H in this case? Reactants are at 100, products are at 20, so it's a delta H of negative 80 kilojoules per mole. Okay, now, if this reaction were reversible, that means I could start with the products, go back up through the activated complex, and wind up back to the reactants. If that happens, I have to be able to move through that activation energy. So notice that in this case, the reverse reaction has a lot more energy involved. I go from 20 all the way up to 130, so the activation energy in the reverse is actually, again, I have to input it, so it's always going to be positive. Activation energy is always going to be positive, but I have to input 110 kilojoules to do that. So this forward reaction is exothermic, pretty easy in the process. The reverse reaction, much harder. Have to put in a lot more energy to get over that hump. But once I get up over that hump, then I can slide down and make my reactants. Now in the reverse, the delta H is still here. It hasn't changed. But in the reverse, what happens to the value? Still 80, 20 to 100, but that's how much energy I have to put in. So in the reverse, because the delta H is a plus 80, it's now an endothermic reaction in the reverse. So if it's exo in the forward, it's going to be endo in the reverse. Delta H is going to be positive or negative depending upon which way you look at it. Activated complexes or activation energies are always positive. Okay, if we compare that to our endothermic potential energy diagram, you see that we've got reactants now lower than products. So activated complex is still pretty high. Let's put some numbers in here. Let's say that this is at 50, this is at 90, and this is at 180. Okay, so as I go from reactants up to the activated complex, how much energy do I have to add? To add 130 kilojoules of energy to get that reaction to work. So an endothermic process always has a much bigger energy of activation than an exothermic process. It's always a much bigger hump that you have to get through. Once I get up there, I make the products, but the products have more potential energy than the reactants. So in this case, the delta H is a positive 40 kilojoules of energy. If we look at this in the reverse, let's think about what's going on. So products to activated complex is the energy of activation in the reverse. That is just 90, but still positive. Delta H in the reverse, still the same value, 90 to 50, but now it's negative 40 in the reverse. I should have put down this was the reverse up top here too. Okay, so the reverse is going to be the same magnitude, opposite sign. Activation energies are always going to be positive, but one's going to be much larger than the other. So this reverse reaction idea is going to come into play more and more as we move from Unit 9 to Unit 10 to Unit 11. So the idea is important. Not all reactions are reversible. We'll talk about which ones are most likely to be reversible, but here's your first foray into that idea. Now, the last thing that this organizer mentions up in the top is the idea of a catalyst. A catalyst is something that you learned last year in biology. It speeds up the rate of the reaction. Well, how does it do that? It actually lowers the activation energy. So I've got one last video here that I want to show you guys to help you see the idea of what a catalyst does. So this is a little bit of review, but then he gets into the catalyst.
A lot about chemical reactions, but what is necessary for a reaction to occur on the molecular level? Collision theory states that molecules involved in a reaction, whether in the liquid or gas phase, have to
A lot about chemical reactions, but what is necessary for a reaction to occur on the molecular level? Collision theory states that molecules involved in a reaction, whether in the liquid or gas phase, have to collide in a particular orientation and with an amount of kinetic energy that exceeds the activation energy of a reaction. This is the amount of energy that has to be provided to allow for the reaction to proceed. Here, we can see that the two molecules have to collide in a particular way in order to react. Otherwise, they will bounce right off each other. As for energy, let's refer to an energy diagram. On these, up means higher energy, and to the right means later in time. So we can see that any reaction will have an activation energy, which is the kinetic energy that the molecules must collide with in order to reach the transition state. This is the orientation which, once reached, the reaction will certainly occur. Collisions with less energy than this will not result in a reaction. From energy diagrams, we can also see delta H, or the difference in energy between the reactants and products. If the products sit lower, it is an exothermic reaction which releases energy. If the products sit higher, it is an endothermic reaction and needs to absorb energy to occur. Most people would refer to a catalyst as something that speeds up a
catalysis
reaction.
typically
While
results
this is
in a
often
faster
true,
rate of
the
reaction.
better definition is that a catalyst is something that lowers the activation energy of a reaction. Because the activation energy is lower, many more collisions will result in a successful reaction, which is why catalysis typically results in a faster rate of reaction. Catalysts do not affect the delta H of a reaction, and they are not used up stoichiometrically.
We're going to pause
in a
there.
reaction. In other words, one
Pause there.
molecule of
Okay.
catalyst
We're going to
can
pause there
facilitate
and
many
go
reactions,
back to
unlike
our
molecules of
organizer.
reactant, which are used up in order to make products.
And so catalysts would lower the activation energy. So if this bottom reaction occurred with a catalyst, I would do something like this on my potential energy diagram to show that a catalyst was used. So whereas before the activation energy needed to be 130 to get this to work, if this were 130, now the activation energy is only 80 to get it to work. Okay, so the activation energy, they sometimes use the prime to represent a catalyst. So EA prime is now lower because the catalyst offers an alternative pathway to get that reaction to occur. So you still have to add energy, but you just don't have to add quite as much. So going back to our organizer, we got one more blank that we're going to fill in with this video. Potential energy diagrams can be altered by adding a catalyst to the reaction. So you've got some problem sets in your binder that let you practice PE diagrams. So please do go take a look at those, and we will see you next time.